Here's a relatively straightforward fluid mechanics problem which looks at the principle of momentum conservation. So this is the kind of question that you could see as a first-year engineering student if you do something like aerospace or mechanical or motorsport or civil engineering. So essentially in this question, we're dealing with a water vane which is stationary. So this is important because that actually means that there are no relative velocities involved anywhere, which is nice. And we have this water jet here, which is traveling to the right, and then it's being turned around completely by this vane, which is being held in place with a force. And that's the thing we have to find. So the question is asking us, what is this force F0 and how do we proceed to find it? So essentially what we do at this point is we draw a control volume, which is sort of like a free body diagram. And for this control volume, we're gonna look at the things which are leaving it, as well as we're gonna look at the forces that are interacting with it. So I'm gonna redraw the diagram. Well, I should say I'm just gonna redraw the control volume. So I'm gonna redraw this dotted square, and then we have a couple of things that are happening. So first of all, we have this force, which is F0, and then we have two other things. So we have momentum flowing in through here, and then we have momentum flowing out through here, like this. Right, so this is, I'm just going to call this momentum in, and this is going to be momentum out. And then we're going to use the principle of conservation of momentum to figure out what that force is. So without using anything like the Reynolds transport equation, which is a more advanced topic, which is also quite useful in the same time, we're just going to apply the very basic principle, which is that the net force, so let's use vectors at least, so the net force acting on the control volume is going to be equal to the rate of momentum out. So this is going to be momentum out dot. So that's like the momentum flow rate out, and then minus momentum flow rate in. So momentum flow rate is given by that dot, and then the arrow means that it's a vector as well. And then we can also define what our positive direction is. So I'm going to say that everything that's acting to the right is positive, and then we can find what everything is. So this net force is given to us by this F0. So that's technically the only external force that's acting on the control volume. And I'm going to write it as minus F0, because the question tells us that the force is acting to the left, so in the negative direction. So I'm going to put a minus in front of it. And then essentially I'm eliminating all the vectors while keeping into consideration the direction in which each vector is acting. So the momentum out is also negative, because as you can see, it's acting to the left. And the momentum flow rate out is just the mass flow rate times the velocity out. So I'm just gonna write it as velocity out for now, like this. And then we have minus, and then momentum flow rate in. So this is positives, which means, we're not going to change the sign from minus to plus. So this is m dot, and then we have v in, like this. So the only thing left to do is to figure out what happens to the velocity, or what the velocity is based on the variables, the symbols that the question is giving us. So we've got this v0 here, and because this jet is completely turned around, it means that the diameter is not changing. So if the diameter is not changing, and if it's water, which is incompressible, it means the density is constant. So if this is constant and if this is constant while it's turning, it clearly means v0 is constant as well. So we can just say that to be the case. So v0 is constant, like that. And that's gonna be basically the magnitude of V in and V out. So both of them are gonna be equal to V0. And then we know that the mass flow rate in is gonna be equal to the mass flow rate out. That's mass conservation, and that's equal to m dot, which is of course this m dot. Okay, and then we can write that m dot as being equal to rho AV. So we have rho, we have the area. So the area is based on the diameter. So it's, if we're dealing with the diameter, it means it's the area of the circle. So that's pi over 4 d naught squared. And then the velocity, which is just v naught, like that. And then we just substitute. So we've got that minus f naught, right? So minus f naught is going to be equal to minus the mass flow rate, so rho, and then pi over 4 d naught squared v naught, multiplied by v out, but v out, we know it's just v naught, and then minus, again, the same thing. So rho pi over 4 d naught squared v naught, again, times v naught. And we can multiply everything by -1 just to get rid of all the negative signs. So we have f naught will be equal to, so we have this quantity which is added to itself twice. So we have 2 times rho pi over 4 d naught squared times v naught squared, which is just pi over 2 rho and then d naught squared v naught squared, like this. And that's the force. So we ended up with a force which is equal to this. Now, whenever you're dealing with this equation and whenever you're dealing with a control volume, what you're actually getting is that this is the force acting on the control volume, on the CV. Now, what I actually mean by that is the force acting on the control volume. This is actually the force that is acting on the water itself. So I'm going to make another note here. So this is the same as saying that this is the force acting on the water jet, basically, which makes sense for the force for the force that's acting on the water jet to be acting in the left direction, because if you think about it, at first, I'm going to draw it here, the water is traveling to the right, and then after it turns 180 degrees, it's acting the other way. So there must be a force which makes it do that 180 turn from going to the right to going all the way to the left, and that force is going to the left as well. It's basically accelerating the water in the other direction. And that's how you do this, and that's the end of the question.